Today, I'll talk about towards safer retinal surgery through chance constraint optimization and real-time geometry estimation. Retinal surgery is one of the most challenging surgical procedures due to its high precision requirements, limited workspace, and the delicate tissues involved. A typical retinal surgery requires an operating microscope to provide the top-down view of the surgery scene. The surgeon will insert a surgical tool and the light source into the eye to operate on the retinal tissue. One challenge for this process is that it is difficult to predict the depth or the distance from current tool-tip position to the goal position. For example, suppose the microscope provides a top-down image like the top middle one. It is difficult to tell from this single image that how far is the tool-tip to the goal point on the retina. However, as we navigate the tool to be closer to the goal, we will see the shadow of the tool shaft and the tool shaft itself will converge to a point. Then we can tell that the tool tip is very close to the goal position. Based on this observation, we consider the shadow as a strong cue for depth estimation during the retinal surgery. In our previous work, we proposed a deep neural network to successfully predict the distance vector from current tool-tip position to the goal position. The input to the network combines a top-down RGB image and a binary user-defined goal image. The output is a 3D distance vector. Based on the prediction of network, we can locate the predict goal position and control the robot to navigate to this position autonomously. However, this method relies solely on the accuracy of network's prediction. What if the predict goal is below the retinal surface? If we keep navigating the tool to this position, it will probably cause damage to the retina, which is what we want to avoid. So based on our previous work, we proposed a method that combines real-time geometry estimation and a chance constraint optimal control to solve this problem. The user is required to select the goal position through mouse click on the screen. Then we fed this goal position into our network and predict the goal point. Instead of predicting the goal position alone, we try to predict a lot of sample points around it. Then we use these sample points to fit a small local retinal area around the goal point. Even though there may exist some outliers, as long as the most predicted sample points are accurate, we are confident about the estimated geometry. When the tool is 2 millimeters away from the goal point, we will use optimal control method to generate a trajectory towards the goal position. The chance constraint is incorporated into the cost function to make sure that the probability of the collision with the retinal surface is smaller than a confidence level, which is set to be 1%. Here is our experimental setup. We tested our method using phantom silicone eyes. We used steady hand-eye robot to control the navigation process, the surgical microscope to provide top-down view of the surgical scenes, light source to generate shadow, and the XYZ linear stage to simulate small translation movements along this axis. The surgical tool we used is 700 microns in diameter. We collected our training data autonomously. This is due to the fixed geometry of silicone eye, and we can estimate the eye center and the radius as close as the ground truth. Some details are on the right. 4,200 trajectories were collected for 2 different eyes, and we changed the eye position, orientation, and brightness every 700 trajectories. Then we trained our network using the same hyperparameters as we used in our previous work. We are using Retinal 18 as our base model, and we modified the input and output size to fit our data. In the next few slides, I'll talk about the method that I used for geometry estimation. We can just focus on the blue boxes here. We are using weighted least squares for geometry fitting, which is considered to have an ellipsoid shape. The ellipsoid fitting is a continuation of the work by Lee's team. In their paper, a general ellipsoid equation is given. They solve this fitting problem using the Lagrangian multiplier method. By setting the gradient to 0, it became an eigenvalue problem which we can solve. Instead of using least square estimation, we used weighted least square ellipsoid estimation in our paper, which is more accurate since the variance of network predictions becomes smaller as the tube approaches closer to the retinal surface. We will show this trend in the results section. We added a weight matrix, the red W, to Hamiltonian equation and solved the coefficients using the same method as Lee's work. After finding the coefficients, we try to find the matrix expression of this general equation. The matrix form will contain useful information that will be used in chance constraint optimization, such as ellipsoid center and ellipsoid matrix A. So both the center and the matrix A can be solved using the equations presented here. When we plotted the ellipsoid, we found that the semi-axis were too short to represent the actual eyeball size, whose diameter should be around 12 to 13 millimeters. So what we did is to add a regularization term to force the estimation to better fit the actual eyeball size. By given the prior information of the approximated eye center and radius, the estimated geometry is much more accurate than previous one. After we have the local geometry information around the goal point, we want to incorporate the chance constraint into the optimal control cost function to generate a collision-free trajectory. To make this happen, we must convert the chance constraint into a deterministic constraint first. Blackmore proved that a linear chance constraint can be equal to a deterministic constraint on the mean of X. To understand this conversion, we can use a univariate Gaussian distribution as an example. The mean mu is not fixed, but the variance is fixed and equal to 1. If we move the mean along the x-axis, we will find that the probability of an event x less than 0 is less than 0.1 will be satisfied if and only if the mean mu is greater than 1.163. This property can also suit for multivariate Gaussian distribution cases. Using this property, we can convert our chance constraint to a deterministic constraint. We assume PC is a good estimation of the eye center following Gaussian distribution with small variance. On the bottom right, PT is the point on the trajectory that we want to generate. LT is the length between the center and the projection point of PT. A projection point is a point that projects the corresponding sample point PT onto the estimated geometric surface along the direction from PC pointed to PT. The chance constraint can be interpreted as the distance between the PC and the PT should be less than or equal to LT minus a small value epsilon. Then we approximate a small area at the projection point to be a flat plane. The nonlinear chance constraint can be approximated as a linear chance constraint using this geometry approximation. By using the property described in previous slide, we can convert this linear chance constraint to a deterministic constraint. To test how does chance constraint affect the trajectory generation, we manually set the goal 5 millimeters below the retinal surface. We can see from the video that the generated trajectory tries to avoid penetrating the retinal surface, which is exactly what we want. By combining this chance constraint method and real-time geometry estimation, we control the robot to navigate to 20 predefined goal positions to check the performance of our method. Here are the results for network training. For the best model of phantom silicon eye, the mean training and the validation errors are shown above. We use the box plot to show the relationship between distance and errors along the 3 axes. A trend is shown that if the tube is closer to the retina, the prediction errors are smaller. We also plotted the distance variance of 1000 validation dataset. which will be used in geometry estimation as a weight matrix. As the figure shows, the x represents the distance to go, and the y represents its variance. The distance is divided into 0.1 millimeter intervals. The different bar color means how many sample points were used for variance calculation. The experimental results are shown in the table. We navigate to 20 predefined goal positions and repeat the blood vessel following tasks 5 times with different waypoints selected. The scalar arrows were calculated by the difference between the scalar insertion point and the closest position on the surgical tube during the experiment. The mean scalar arrows are all within 300 microns. The mean arrows along XY axis are all less than 90 microns, which meets the requirement of retinal surgery. Here comes our conclusions. We show that chance-constrained optimal control can help generate a safer trajectory for autonomous navigation tasks in the retinal surgery. Our next step is to extend our experiment to the pig eyes to get prepared for the human eye test. That's all I want to present.